Hang on.
I'm a showstopper, huh?
Wait a minute,
Yes, you are.
Isn't Daryl our current president? Doesn't he start the meeting?
I just did, didn't I?
Oh, that was
I think
you.
so.
Oh, sorry about that.
Yeah.
But we can't really start without Tim.
It's the long lasting effects of anesthesia in my case.
I'm going to be starting meetings from my grave.
Oh my God.
To get an uplink on your gravestone.
Okay, guys, this meeting is live streamed to
We'll get you
YouTube now.
Wi-Fi,
Okay,
Tim.
good.
Okay.
Tim, I swear, if over your grave I see a Wi-Fi connection, then I know you're up to something.
Yeah,
Okay.
fire up your cell
Well,
phone.
welcome everyone.
Hi.
See what's on our agenda. So everyone, make sure that you fill out the door prize entry. Spencer, you're going to drop that in the chat.
Yeah, hang on. I'm still trying to get organized, so I'll drop that in the chat in just a
Okay,
second.
he'll drop that in. Take a look in the chat. Sign up for the
Okay.
door prizes.
Oh,
And that-
a notice did not go out stating who the speaker is and what the topic is. I never received one.
It got
Didn't
out
go
very
out
late.
I'm gonna speak forever, and Tim will let me know when I've done something wrong.
Well, I think it went out, but it went out very late. We did not get a response from our speaker that we thought we might have. So Tim is filling in, and he is going to talk about Deep Field and I think a little bit about James Webb as well. So we'll get to that. I don't know if there's any big announcements. We made a lot of progress on our donation of our shed. We were able to take that apart, take it down, move it to Lockwood, and it is there waiting to be set up again. So the people who didn't have any information on what was going on with that, it worked out really well. We had a member of ours who's a little more infirm now than he would like to be, had a nice roll-off roof shed in his backyard, and he could not use it anymore. So he donated it to the club. It just took about a few days and about 10 guys to actually take it apart and move it. But it went
Did
well.
anybody take photographs?
Yes. I might have some that I can show you. Maybe we'll do that right at the end. I'll look for them in the meantime. We could do a committee reports. And I'll look for the pictures while we do that. Spencer, you want to do, are you ready for Treasury?
New members, guys. Any new members? Daryl, do that first.
Sure. Do we have any new members here? Hands? No? All old members?
This
I
is
see
Roman.
Simon.
I'm
I
a new
haven't seen
member.
Simon in a long time. Hey, Simon, how are you?
I think Roman's the new member.
Correct. I'm a new member. Can you guys hear me?
Roman?
Yeah.
I'm trying to speak, but maybe you can't
Yeah.
hear me.
No, I hear you.
All right, great.
Roman, are you there?
Yes, I'm here.
Are you a new
Welcome.
member?
I am a new member. Just got my membership approved a few days ago.
Fantastic. Tell us a little bit about why you joined and how you found out.
I mean, I've been watching you guys for a long time. I just decided to kind of join up and be part of the hobby.
I got some background noise on somebody's mute. Can everyone mute who's not speaking, please? All right, thanks. Go ahead, Roman.
Can you guys see my my webcam?
Yeah, we see you.
All right, very nice.
Hey, you're there.
Okay. Yeah. So yeah, I've been an kind of amateur for a long time. I kind of decided to join the club. I don't know what you guys want to know. My interest is primarily astrometry for asteroids. I kind of have a backyard setup that I use for that.
Great.
So I'm interested in kind of doing more, making
Okay.
use of the dark side, and maybe make it
Congratulations,
one
real
day.
science.
One of the things that you can do is when we are doing outreach, especially for Boy Scouts, sometimes we'll have our members set up on their own systems in their own backyards, and they will share their screens on a YouTube. Is that something you might be willing to do in the future?
I don't see why not. Sure.
Okay. All right. We'll keep you in mind for that.
Yeah, sounds good.
Any other new members here? Thanks, Roman.
This is Jeff Seidel here. I'm not a new member as of this month, but this is my first time actually making the Zoom meeting. So hey, everybody.
Hi, Jeff. How new are you?
I want to say a couple months.
Okay.
Yeah, I was quite excited when I got that pin. So I think I remember that was a couple months ago.
All right, great.
And I joined because I was part of the New York Amateur Astronomy Society, and then I moved to LA. So figured I would join the LA one.
I think I remember seeing your notes in your application that you were that. Well, welcome here. It's probably just as bright here as it was there.
Yeah, it's a little bit better here. It's okay, good. less
And
condensed.
unfortunately, the pizza is not as good.
Yeah.
And we have a dark side that you can go to now. So, all right. Anybody else? I think there's just the two.
I thought I saw.
I'm quasi new. This Randy. I was at the shed demantling.
Ah, I don't see you. Are you?
At the top.
Right here in my living room.
Oh, there you are. Did you go out to Lockwood as well?
I did not. I had a commitment for that evening.
Yeah, me too. Okay, well, good. Well, thank you.
Yep.
And thanks for everyone else that was here that helped us do all that too. It went surprisingly well, I think. I don't see John. I don't think John is going to be here tonight either.
No, I
So
don't
we
think
won't
so.
have a treasury report. However, we're doing fine. The membership is staying strong, and we have money in the bank. We are able to do projects, so things are okay in that arena. So next month we'll probably have a full treasury report.
Any more new members? I think I see Justin. Are you?
I'm still relatively new. This probably be about 2 months for me. This is
Okay.
the second meeting I've attended. I just did the Mount Wilson night a couple weekends ago.
I was just going to say, I recognize you.
Yeah, that was awesome. That was so well put together and so fun. Blew my mind.
This is what we want to do. Well, good. How did you find out about us, and what circumstances that you said, oh, I got to do this?
For the club or for the Mount Wilson thing?
No, from the club. Mount
For
Wilson's
the
pretty
club,
obvious.
club, I've always been super into space. My uncle, he worked, he designed the helmets for one of the Gemini and one of the Apollo missions. So
Wow.
he talk about that with me when I was a kid.
Awesome.
My dad force fed me Star Trek as a kid, and then recently when I moved out to LA, randomly I had won some money in Las Vegas. I decided to purchase a telescope with some of that money, and I realized I didn't know how to use it, and that's when I got connected with you guys.
What you got? What you got?
And
Right.
it's been super fun, and everybody, the few times I've been out to Garvey Ranch, everybody has been super helpful, and it's been fun.
Great. Thanks for the feedback. All of the new members should go to Garvey just to check it out. It's a great place. Meet a lot of the core members of the group, hang out there a lot.
That drive home at night from Mount Wilson was a little intense.
Yeah. Well, it's why we want to make sure that everyone gets up there in the daytime, so at least they see it on the way up.
Yep.
All right. Spencer, we got a secretary report?
We're very, very brief. We are close to 870 members now.
Oh.
So
And we only have 33 here. Okay.
So that's so basically, and I'm a little late in getting the renewals out, but we're doing really, people are I'm finding I'm having fewer and fewer people to drop off the roster for lack
Wow.
of renewals. So that's
That's
good.
amazing. That's bigger than OCA, I think.
Well, this is good. I mean, we must be doing something right if they're coming and staying. So
Yeah.
This is good. We will keep
Yeah,
it up.
absolutely.
We will keep it up.
Okay.
Let's see.
Let me slip in something about the dark sky petition.
Yes, please do.
Okay. So This is, everybody's able to see the screen. So we have a petition on change.org, and we're up to 910 signatures now. So we've gotten support. This is primarily, working with Rod Kaufman and John O'Brien. So the three of us have been huddling on, working on this for a while now. And if somebody else would like to join us, more than welcome to have, we welcome the help. So that, right now, so mostly thanks to Rod, he's gotten support from the Center for Biological Diversity, and they started a petition similar to ours. And then he contacted local Audubon Society. They're really concerned because the pollution, light pollution, has a major impact on bird migrations. So they're also circulating our petition. At the same time, they're helping push a bill through the Assembly, AB 2382, which basically mandates that, well, I guess I'll be, to be a fairly imprecise summary, is that they're going to try and shut off the unnecessary lighting on state buildings at night. There's more to it than that, but that's a one sentence or a 10-second summary of that. So in terms of things that you can do to help, and I'm going to be drafting an email that goes out to the LAAS membership. But if you live in LA County, we need you to contact your supervisor to let he or her know that you support our petition, and also contact your state assembly person to voice support for AB 2382. So I'm in the middle of drafting templates to send out to the membership that you can use. So you just drop your name in it, and feel free to modify the template to suit your personality, your style. But the whole, it's moved to the point where it's now a political issue, in the sense that we need to get the politicians' attention, and the only way to get their attention is to have people send in emails or US mail, call them up and say, hey, this is something I'm really concerned about. And at some point, it'll hit a point where they'll start paying a lot of attention to it. Like, I contacted my supervisor, and she referred me to the LA County Building and Safety folks. Well, they're the ones who initiated the dark sky ordinance in the first place. But then they said, well, yeah, thanks, we got your email, but until this gets a lot more supervisors' attention, there's not a whole lot we can do about it. So
Vincent?
Yeah.
I've written a couple. I know I've written at least 2 letters in the past, but it just occurred to me, do you want me to email anybody in LAAS letters when I write them?
Not, I mean, it's nice to have copies of them, but it's not, not a requirement. It's just, but so thank you for your support.
You're welcome.
Okay, and somebody in the chat asked where the petition is, so I'm just going to copy it here and paste it in the chat. So I'll put, oops, I'm sorry, I can't do that there. I'll put it in the chat. It's but if you can see the slide I'm sharing, it's change.org/preserve dark skies. But I'll also post it in the chat. Okay, well, thank you.
All right.
That's my pitch. And by the way, if anybody would like to join us on working on this, I'm more than happy to have help. We meet every other Tuesday at 3 o'clock via Zoom. So just shoot me an email at secretary@laas.org. Okay, thank you.
All right. Any other questions or announcements from any other sources?
Okay.
No?
All right. And
yes,
Daryl?
yes.
Real quick, there's a public comment section. The LA County Board of Supervisors has their meeting. I think it's once a week, but if anybody ever wants to speak on the issue of light pollution in LA, you can go down there any week that they're meeting, which is most weeks, and just sign a little clipboard, and they'll let you speak for 5 minutes on the issue.
No, well, they've
That's
actually
just another way to get attention.
they've changed they're no longer taking those that in person. It's via Zoom, and they're limited to 1 minute.
Okay.
And you have to actually get on the, they'll open up for signups near the end of the month. You have to get on the list and
Oh,
sign up. So we're trying to do that. And so that's one of the things that we're trying to do is, it's going to take multiple presentations to the Board of Supervisors to get their attention. So you have to hit it on multiple fronts, in person or,
no, I don't
presentation.
think it was ever 5 minutes. I think it was 3 minutes they used to let you.
Yeah. It's down to 1 minute now.
Okay. Thank you.
Okay, and somebody else pointed out, I'd forgotten that the petition link for the petition's at the top of www.laas.org. So it's on our website. So just click there. Okay, thanks.
And I just saw an email from our furry face Jack in Denver about some interesting stuff that we are going to do the same. I think it's the lighting ordinance there too. They passed something there that we'll probably take a look at. I thank them for that. So we'll look into that too. All right.
Yeah, hello. Yeah, Jack.
Yes, Jack. Yeah.
It's an ordinance or a bill that was passed through our politicos, and it allocated $35,000 to the Tourist Bureau, aimed at and earmarked for preservation of dark skies. And I was told that it sailed right on through. So I posted a note about that on our forums.
Yeah, that's where I saw it. Thank you, Jack.
Goody.
It was good information, and our Tourist Bureau ought to get a call too. I'll see if we can look into that as well. I mean, we must have one here for Los Angeles, and they're probably not all that happy about how light it is. We'll stay on this. It's good. Anything else? Otherwise, I'm going to start handing it over to Mr. Thompson, our speaker for this evening, who is going to talk about the Hubble Deep Field. Thank you for stepping in tonight, Tim. I know that we had a speaker or almost had a speaker and didn't. So if there's any last questions, otherwise, Tim.
All right, Tim.
Daryl?
Yes, sir. Yes.
What about the committee reports?
We had them, Curtis.
Oh, I didn't hear any of them.
I'm sorry.
Well, I just wanted to mention the Ford.
Oh, okay.
We're planning on opening Ford Observatory over the Memorial Day weekend, and we've got to check the accessibility of the roads. We can easily handle high ground clearance vehicles, but I'm not sure about cars at this time. Joe will be up there this weekend, and he'll check it out this weekend, check the road conditions out. So that's our plan to open up for Memorial Day weekend.
Curtis, is there any long-term plans for the road to get better?
No, well, it has nothing to do with us. It's forestry.
It's forestry. Okay.
Yeah,
All right.
forestry. I think the problem is we have a lot of rocks on the road this time around. Joe and I both had our low ground clearance vehicles last time, so we couldn't go up there last weekend. And Joe was going to bring his truck up, and I get my Hummer available, and we'll check it all out. But the road is, I think the forestry does plow the road, and I think they do it for fire safety. There's another issue there. There was a big log, a big tree that fell, and it's partially been cut away, but it may still be a problem for wide vehicles. So I think the forestry may do something about it, because fire trucks may not be able to get up there very easily.
Curtis?
Okay.
Yeah.
Quick question. How long is the road to Ford?
About a little over 3 miles.
Thank you.
From Table Mountain Road.
Okay. Thank you.
It's about 3.5 miles, something like that.
Okay.
Okay. Thank you, Curtis.
Okay.
It's a nice narrow 1-lane road most of the way, and you try not to drive off the mountain.
It is a paved road, though. That's the nice thing about it. It is paved, but there's a lot of times we get a lot of rocks that fall onto the road, and they got to be taken off. We had, like I said, there was a fairly good sized tree that fell across the road, and it was cut open, but it could be a problem for fire trucks to get up in that area. And we have had I think Joe was up there one time. Joe, do you remember that time you were up there with Greg and you had a fire on a tree, lightning hit a tree or something like that? You there, Joe?
Yeah, I'm here.
Yeah.
It was about a couple miles from us. We smelled smoke and saw it, and then the fire trucks came up. But we found out it was a tree that was just smoldering, and they had been working on it for a couple of days. They were coming up to check it again to make sure they really got it out. And we went on a road a couple of weeks ago, and it was pretty clear, other than the tree that Curtis is talking about. There were some rocks that came down, sharp ones, but nothing that a car wouldn't clear. But
Yeah, we got to make sure, because I think the concern we had was the fact that you got to have good tires. I'm
going to take a push broom up there and push anything off. The
Okay.
snow brings a lot of rocks down.
Okay.
All right.
Where's that at?
Ford Observatory in Wrightwood,
Oh, okay.
not too far from Table Mountain.
We'll have an announcement.
In fact, we can see Table Mountain from Ford. The Table Mountain Observatory, JPL's facility.
We'll
It's
get
easier-
Andy to post an announcement with directions and stuff.
That's the plan right now, yes.
Yeah. It's easier for those in the eastern part of LA County to get to than to get to
Lockwood.
the Lockwood site. It's a lot shorter.
Okay. All right. So there's no Lockwood report. John's not here. And Kevin, is there anything that you know about Lockwood that we haven't heard recently?
My memory is so short. John just had shared something. I guess it was just really about the Rolloff Roof, and thanking people for their efforts. So let's just reiterate that. Thank you very much. But in the future, there not exactly. I don't think it's scheduled yet. But we'll need help for assembly.
Assembly, yeah. And we're gonna put some concrete.
Shall we say?
Pour some concrete first.
Concrete first, yes. So if anybody is interested on Groups.io, we encourage you to sign up to get messages for the Lockwood Committee. If you're at all interested, either as participating on in the committee itself, or if you want to add some your own muscle or tools or anything like that, that will be the place to get your information.
Okay, good.
The schedule.
Oh, the update on Starlink, we have the permanent antenna mounted, so we are officially off of Viasat and on Starlink. So it's a love-hate relationship.
It works awesome. It works awesome up there.
It was the right thing to do.
Yes.
All right. Well, with no further ado, then I think if there's no other announcements, or let's get Tim started. Tim?
Oh boy, don't say get me started. Well, let me share my screen here. If this, no, not that. That's what I want to share. Okay, let's share that. Then let's do that. And in theory, you should all be able to see my slide that says Hubble Space Telescope Deep Field Images. I hope you can. Good. Before I start my regular talk, there's a couple of things I want to say in terms of announcements, perhaps. And of course, my internet connection is unstable, so my voice may go weird on occasion, but it still seems to work. On Thursday morning at 6 o'clock, for those of you who are early risers, the European Southern Observatory is live streaming a press conference, which they say will announce a major new Milky Way result from the Event Horizon Telescope. Those are the people who gave us the picture of the black hole at the core of M87 back in 2019. It seems evident that on Thursday morning, they will open up their picture of the supermassive black hole at the middle of the Milky Way. And so I think by Thursday, we'll know what our Sagittarius A star super black hole will look like. So keep your eyes open for that. And of course, Sunday is the 15th, and there's a total lunar eclipse. I think the totality phase lasts from something like 8:30 to 9:50. Moon rises already in penumbral eclipse. We have some volunteers who'll be going to Griffith Observatory, but there'll be 10 million other people there. And I'm personally going to Garvey, and several of us will be going to Garvey, which will be open for the eclipse. So if you're not interested in looking at the moon from your own backyard and your own telescope, you can come down to Garvey. And so with that said, the Hubble Space Telescope Deep Field Images is what I'm going to talk about. And I've been trying to get this old ancient talk in shape. That's why I was a couple of minutes late getting into the meeting. And so hopefully I've managed to make it work. Well, here is the original deep field image that came out in 1996. Amazed everybody. About 5,000 galaxies in this field of view. If you recall, when the Hubble Space Telescope launched, it launched with a fantastically precise, but unfortunately inaccurate mirror, which was very precisely ground and polished to the wrong shape and did not focus. Astronauts had to go up and add optics, put glasses on the telescope. And that's why the image has this funny shape with a notch out of the upper right corner, because that part of the field of view is blocked by the extra optics they had to put on in order to make the rest of the image look good. And so here are the specifics for that. It's a total exposure of 155.25 hours in the 4 filters. The wavelengths are given there. The range from about 305 to say 700 nanometers is the range of human vision. So you can see there's a little bit of ultraviolet, just a little bit too blue for humans to see, and a fair amount of infrared. Very small area, but it was spectacular success. And here is some details. You can see there are, most of the galaxies just look like smudges. We're all used to the great pictures of fantastic spiral galaxies and in-your-face galaxies. But the galaxies that cosmologists look at are tiny smudges that everybody else would walk away from bored, but cosmologists jump up and down and get excited about. But still, you can see there's quite a lot of detail on very distant galaxies. You can see the closed spiral galaxies, the barred spiral galaxies, the elliptical galaxies, galaxies interacting with each other, all fairly visible in these blow-up details of the image. When you look at an image like this that just shows you the overall image, you miss a lot because there are a lot of small things in there that you just can't see all that well because the image isn't big enough. And so when you have nice close-up sections like this, you can see there's quite a lot of detail. And here's a census of the things that were found. The original image was where the 3,000 galaxies were found. The J and H bands are extra long wavelengths, and added quite a few galaxies, and deep red 300 more. So about 5,000 galaxies in the field, around no more than 20 stars down to 26 magnitude. and a few other sources, a couple of supernovas, some X-ray sources. What's really interesting is that what they did was take the telescope and point it at what amounts to the emptiest piece of sky they could find. If you submit a proposal to a telescope time allocation committee, say, I want to spend a whole lot of time staring at some empty piece of the sky nobody's ever looked at and find out if maybe there's something there, it won't even survive the first glance from the time allocation committee people, because the proposal requests that are submitted usually oversubscribe the time available on the telescope by at least a factor of 2, probably more. So the competition is fierce. However, the astronomers who manage the projects, like the management for the Hubble Space Telescope, those scientists no longer have any time to submit proposals to anybody, which would mean they can't do science. All they can do is manage, and they don't like that. So the scientists quit, or scientists say, no, I don't want to do it, or whatever. So in order to grease the skids, we have what's called director's discretionary time. And whoever the director of the telescope is, they can do whatever they want with that time. Now, there are probably a few restrictions, like, no, you can't point the telescope all the stars of Orion and go through them alphabetical order while you have a party in the office. That's not going to work. But if it's remotely reasonably scientific, we can do it. So the Deep Field project was initially funded using discretionary time from the director. So it's because it's a project nobody else would be able to do. And it doesn't follow your usual high school version of the scientific method, where you have an hypothesis, then you design an experiment, you test the hypothesis, whatever results you get, then you go back and that's a perfectly valid way of doing science. Scientists do it all the time. But there's another way of doing science, which is what I like to call the Thomas Edison method. You take the red wire and the black wire and you tell everybody, I wonder what happens if we put these two together. Everybody stand back and you just stick them together and find out what happens. That's a pretty good way of doing science too. And we do that. And that's what this is. Let's just stare at some empty piece of sky and see what happens. And who knows, maybe they would only see 1 or 2 galaxies and they'd all go, well, that was a bust. But that obviously did not happen. They saw 5,000 galaxies and everybody was terribly excited. So they went about selecting the field very carefully. And I remember emails coming around asking various astronomers, what do you think? The field of view needs to be in what's called the continuous viewing zone. The Hubble Space Telescope, like any other space telescope, can't point at or too close to the sun and needs to have its solar array pointed towards the sun. And so if you go up near the celestial poles and look far away from the ecliptic, the telescope can go around the Earth and constantly keep itself oriented so that it's looking at that field of view without any break. If you go to a lower field of view, the Earth gets in the way, the moon gets in the way, the sun gets in the way, and so you can't constantly stare. You have to come back and do your observing in bits and pieces. In this case, they wanted to stare constantly at this one spot. So they knew the field of view had to be in that area. They knew they had to have low optical extinction, and that means you're not looking through dust clouds and things in the way. And in fact, the field of view has no optical extinction at all. Hydrogen column density, H1 is neutral hydrogen, just tells you how much hydrogen gas are you looking through. So like what line of sight through the Milky Way galaxy, you'll be looking through a lot of hydrogen, so you want to get away from the plane of the galaxy. And so they set a limit of 2.5 times 10 to the 20 per square centimeter. And what you're doing is you're looking at a column that has 1 square centimeter of area and like 200,000 light years of length. It looks pretty weird. And then gathering up all the hydrogen in there and so how much do we have? Particularly need a low amount of foreground infrared emission from cirrus, which is loose dust scattered around in the galaxy, and of course zodiacal dust as well. Of course, you want to avoid all bright sources because you're deliberately looking for a really empty, dark piece of sky. And you want to exclude all the nearby galaxy clusters because a galaxy cluster will increase your H1 column density and probably the cirrus emission as well, or interstellar intergalactic emission from the galaxy cluster. So with all these criteria in view, they looked through all the sky surveys, came up with about 20 candidate places they could look, and then had to weed them out. Most of them they ditched because there was too much cirrus. They used the old IRAS imagery at 100 microns and threw out all the fields of view that were no good. And finally wound up with one that was chosen primarily because while it fit all the other criteria, there were guide stars available, which made it a lot easier to control the pointing of the telescope. Those of you who are imagers and have to use guide stars understand that. So here's where that field of view is, just above the bottom of the bowl of the Big Dipper in Ursa Major. There's the RAN deck. If you're anxious at staring at the Hubble Deep Field yourself, you probably won't see most of what was seen in the Hubble Deep Field, but you're welcome to look there if you really want to. So in preparation for this, not only here you see the Hubble Deep Field North on a field of view from the Mayall 4-meter telescope at Kitt Peak. But aside from staring for a long time at that one field of view, HST also spent a couple of orbits in each of a number of flanking fields to make sure you have a census of the objects around the field of view. So if you find something, say at the edge of the field of view that's interesting, okay, you've actually got some data you can look at to see what is that, or if you think some light is escaping into the field that shouldn't, just so you can put the field of view you're looking at in some kind of cosmological context. You know what's going on around it, so you know where surrounding galaxy clusters or galaxies might be. If there's anything peculiar about that field of view, then you'll spot it and you'll be able to compare it with what's going on around it. And here's what the HDF field of view looks like in the Palomar digitized sky survey images. Not much there. Cosmic strings, which are also hairs, I think, on the old glass plates, or got into the photocopier. A few objects, but not much. So you can see it really is a pretty empty piece of sky on the Palomar sky survey images. Well, that was such a spectacular success that they decided to do it again. And here is the HST South deep space image. And here are the particulars. The exposure time was not as high, same filters, so the same wavelengths, but less exposure time, same area, roughly the same size as a dime held at 75 feet, which is a long ways away. Okay, here's a dime. I got a dime, right? There's a dime. Hold that dime 75 feet away, and that's the size of the piece of sky you're looking at, not much. So that's why there are only 2,500 galaxies in this image instead of 5,000, because the exposure time is significantly less. Up the exposure time and you'll get more galaxies. And this is where the southern field of view is in Tucana. Now, after the HDF North was made, 2 new instruments were attached. NICMOS and STIS spectrometer, so you can see the outline of the image of the regular deep field here, and then NICMOS is down below it, and over to the left is STIS, and this is a Cerro 4-meter image showing that piece of sky. The relationship between the little fields of view of the other two instruments and the wide field camera 2, which has the typically funny HST shape, is fixed. So you can rotate the WIFPIC 2 image to move where the image field of view of the other instruments are. And the STIS field of view was directly chosen because there's a quasar there. So this shows you the relative orientation, what NICMOS is looking at in infrared. Almost everything in the NICMOS image, in fact, literally everything in the NICMOS image is invisible in the optical. 0.8 microns is too long for eyeball vision. So this is a pure infrared image. STIS works throughout the visible and into the near infrared. So most of what you see in the STIS image is visible in a visible light image. And so here's what the NICMOS image looked like. And see, these are galaxies, about 335 objects cataloged, most of which are galaxies, a few foreground stars, all entirely infrared observing. And of course, the resolution isn't terribly great, but still you can see there's a barred spiral galaxy and a number of edge-on galaxies, a few foreground stars with diffraction spikes still in infrared. Perhaps even more interesting, the quasar J2233-606 is in the STIS field of view. And that's the primary reason for choosing this field of view, was to look at this quasar. But there are some nice galaxies here, and there's a couple of interacting galaxies over here. And I don't know if they've already previously been cataloged or if they've been studied, but they're obviously two interacting galaxies that would go in the ARP catalog if ARP had been able to see them. Now, the quasar is interesting because quasars are high redshift objects and they're very bright. And what you're looking for is something I've called the Lyman alpha forest here. And I'll just digress for a slide to show you what that means. And this vertical diagram on the left, this is, of course, is the Hubble Deep Field, representing now or back then. Way up at the top, this red stuff basically is the cosmic microwave background. So when the universe finally cools down enough to form neutral atoms, the cosmic microwave background is cut loose. The radiation and the matter disconnect from each other. And you have this period called the Dark Ages, where there's no visible light. It's all much higher wavelengths because the universe is very hot, but no visible light, and everything's neutral or no ions. So once you get to star formation begins, the first galaxies, these yellow-green dots start showing up, and these are bubbles where the new stars, new galaxies first forming are ionizing the gas around them with ultraviolet light. And as you come towards today, you get more and more of them. And if you look at the panel on the right, you have your quasar, the red dot way over there. As you stare through more and more of these ionized bubbles, you get more and more of these spikes on the graph of intensity versus wavelength. And you can see they match up with the diagram above. So where there's only a few dots, you only have a few spikes, and then where there are a lot of them, you have a lot of spikes. These tell you when reionization occurred, which is a goal for the James Webb Space Telescope, for instance, to observe these kinds of things directly. Here, you're finding these little bubbles by looking at this graph. but you'd like to see them directly if you can. And the James Webb Space Telescope is going to try to do that. And whether they succeed or not, we'll see. But the telescope is in good shape to do that. So next came the Hubble Ultra Deep Field. Now, by this time, the success of the northern and southern fields had convinced people this is a really good thing to do. So we're all going to do deep fields. The Chandra X-ray telescope went off and did an X-ray deep field. Everybody is doing deep fields. Well, the ultra deep field, they had yet a new instrument, the Advanced Camera for Surveys, which could look at much longer infrared wavelengths. Means they could see higher redshifts, and of course they could also see dimmer things. So they decided they would do a deep field, and they selected a field that cannot be in the continuous visibility zone, continuous observing zone, because the long infrared wavelength, if you have the telescope tilted up so that you're in the continual viewing zone, you now have the Earth off to the side of your field of view. At optical wavelengths, nobody cares, works fine. But in the infrared, now you're dumping infrared into your telescope, and it actually brightens the field of view. So you need to turn the telescope so that you're not looking at the Earth. And this is the reason the James Webb Space Telescope went out to the Lagrange point, because it's really hard to do infrared astronomy from Earth orbit, because the Earth just is a huge bright source and gets in your way all the time, and the moon gets in your way, and you just got to get away from it if you want to do it. But they were stuck in Earth orbit, and so they picked an appropriate field of view so they wouldn't have to worry about bright time caused by the Earth. So they had to get up maybe halfway between the poles and the ecliptics, and they decided they would just point at the same place the Chandra X-ray telescope had pointed to, called the Chandra Deep Field South. It had already been observed by the Chandra X-ray telescope in 1999 to 2000 over the new year. Remember that the original Hubble Deep Field came in 1995 and was announced in 1996. And it was so successful, the X-ray people decided they'd do it. And so Chandra X-ray telescope did a deep field in the south, and the European XMM Newton X-ray telescope. The Spitzer Space Telescope observed that field of view, and the Great Observatory's Origins Deep Survey. So by this time, there was a field of view several different telescopes had looked at, and they picked that field of view for the ultra deep field. And here it is. So in this case, you're looking at 400 orbits, ACS exposures, much longer exposure time, 267 hours, just shy of 1 million seconds. And so in this case, there are about 10,000 galaxies visible in this field of view, double the number available in the original Hubble Deep Field North. The field of view is a little bit bigger for ACS. You can see that the characteristic notch in the corner of the old HDF images is not there. When the ACS was installed, it had the corrective optics built into it, so they could take off the additional optics that were built on to correct the image for the wide field camera 2. And so the notch is no longer necessary, and you have a nice looking ordinary image. And the Hubble Ultra Deep Field is the one that's gotten the most attention since the deep field era. And that was so successful that they just kind of went crazy and did all kinds of deep fields. And I'll go over them in a minute. But first, I want to take a minute to look at the original deep field. That's the HDFN. The southern deep field, HDFS. And what you're looking at here on the top line for the the top two lines. The top lines are exposure times in hours. So for each channel, for HDF North, F300, 48.93 hours, 27 hours for 606 on the southern image. And what I've written out here on the side is, suppose you wanted to do that all sky. Like if you want to do the same deep field image, but now I want to cover the entire sky. So I'm going to stare for a long time here, then I'm going to move it over, I'm going to stare for a long time, and the whole sky. Remember, dime held at 75 feet, it's like 2.5 arc minutes on a side, and you're going to cover the whole sky. If you did it perfectly with no overlap, it would take you 7,615.7 years of exposure time to do that if you wanted to recreate the original Hubble Deep Field results. That's not accounting for any overlaps where you overlap the fields of view. Doesn't count for downtime of the telescope. It doesn't account for data transmission time and all that good stuff. Obviously, no one is going to propose to do that anytime in the near future, especially because you hope your space telescope lasts for 7,600 years, which is a lot of Hubble servicing missions. I don't think that's going to happen. And then the next group here shows you the limiting magnitudes. The AB magnitude system is unique to the Hubble Space Telescope, but it is not significantly different than the magnitudes, Johnson or Cousin magnitudes that you're used to using. And that sources this dim, they're essentially the same thing. We're looking at 26 to 28th magnitude, which qualifies as really dim by just about anybody's standards. Now, the bottom shows you the exposure times on the top lines and the limiting magnitudes for the Hubble Ultra Deep Field with the ACS, which has different filters and a lot more exposure time. To recreate that image all sky would take you over 8,000 years of exposure time. So if you ever wondered why didn't they do that, why didn't they just stare at the whole sky and do a deep field image of the whole sky? Now you know why. Thousands of years of exposure time prevent you from doing that. And they're looking at as deep as 29th magnitude in the ACS Ultra Deep Field, which is really pushing it down there. I'm not an expert on typical imaging telescopes and what kind of limiting magnitude would you get, but I'm willing to bet 29th magnitude would challenge just about any imager. So there was a new Hubble Ultra Deep Field in 2009, which pushed the limiting magnitude to 29.4. So what they did is they took the old Hubble Ultra Deep Field and added some new data from the new Wide Field Camera 3, which looks in the infrared. So you're just stacking images. You're taking all the old images you had and then stack some new images on top of them, and that beats down the noise, enhances the signal, and you're able to push your magnitude a little bit deeper. And then they went to the extreme deep field, and they're running short of titles for their fields now. We've done deep, we've done ultra deep, we've done extremely deep. It's running out of names. About the same field of view, 5,500 galaxies. Here, what they did was a lot of observing programs happened to look in that direction while they were busy doing something else. They were not deep field exposures. Nobody was trying to do a deep field. They just, people were looking there. So they took a whole bunch of years of observing projects, looking at that area, and stacked them all up. And so the limiting magnitude is not consistent throughout the image. In some place, the limiting magnitude goes down to 31.2, which is really, really dim. But at other places, it doesn't go down that far because you didn't have any images to add up for that place. But if this is a typical field of view, it implies over 177 billion galaxies all sky that would be visible to the Hubble Space Telescope if you could do this over the whole sky. But in this case, it would take you nearly 14,000 years of exposure time to pull it off. So that's not going to happen either. And I point out that 31st magnitude is only 7,585,000,000 times dimmer than 6th magnitude, which is the dimmest thing you can see with your naked eye. So when we say dim, that's what we mean by dim. So the next one is a real ultra deep field exercise. They did it again in 2012, which is basically called the Hubble Ultra Deep Field Infrared. And so now they scanned the whole image field of view again with wide field camera 3 with new channels and a lot more data, 128 orbits of new data. So now consistently throughout the field of view, you're down to almost 30th magnitude, 29.5 to 29.98. Might as well call it 30th. Here, what they're trying to do is to dig out the very high redshift galaxies so they can see what the role of galaxies is in reionization, all those little green dots you saw in the image talking about the Lyman alpha force. Again, 10,000 galaxies at least, maybe 10 or 20 stars. You can see some of them because of the diffraction spike. But virtually everything you see in the image is a galaxy. And again, you note some of them look really good and really obvious: spiral galaxies, elliptical galaxies, irregular galaxies, but most of them are smudges. Remember that cosmologists love the smudges because those are the really high redshift distant galaxies. And they extended it into the ultraviolet. And so 2014, they added ultraviolet to this. It's a slightly larger field of view, 10,000 galaxies in this field. And that implies 355 billion galaxies all sky, visible to the Hubble Space Telescope, if you could deep sky the entire sky, a lot of galaxies. So that's basically a minimum number of galaxies in the universe, in the observable universe anyway. The real number is probably as much as 10 times greater than that, because there will be so many dwarf galaxies that you just won't see because they have low surface brightness and they're just too dim. And again, the limiting magnitude just depends on the filter, goes around 28, 29 pretty consistently, and 90 orbits of new data. And in this case, it's ultraviolet data, and ultraviolet clues you in on star formation. So in the previous exercise, they were trying to figure out how galaxies are involved in reionization. In this case, they're looking for high redshift star formation. And finally, they come up with the Hubble Legacy Deep Field, slightly less than 1/4 of a degree across. Now, this field has 265,000 galaxies in it. It is not imaged as deeply as the other fields, but it's very big. And by very big, I mean nearly the size of the full moon, nearly 1/2 a degree across. So the legacy field implies 58 billion galaxies visible if you did this same exposure over the entire sky. But again, it's going to take you thousands of years to do that. Nobody's going to talk about that. And it's really the 177 billion galaxies of the extreme deep field, or the 355 billion from the previous deep field, that are the real numbers you want to know if you're thinking about how many galaxies there are in the universe. The Hubble Legacy Field is now the home ground for everybody doing any kind of deep field exercise. The little blue box in the middle shows you the size of the extreme deep field. The Hubble Ultra Deep Field, the ACS image, is the red box, considerably bigger than the extreme deep field. The Great Observatory's Origins Deep Survey not as deep, but still deeper than normal, covers all that sky inside the red. And the legacy field is not a nice square field because it's not staring with one field of view of the instrument. They've dithered the telescope around and exposed a big chunk of the sky. So it has a very funny shape. It has notches carved out of it. But this field of view is where everybody's going to stare. And although nobody is talking about it, it's virtually certain, you can bet hard money on it. At some point, the James Webb Space Telescope will stare into this image, probably somewhere in the red square of the Hubble Ultra Deep Field image, just because there is already so much data available in that image field of view. If you combined it with whatever you get from the James Webb Space Telescope, you would come up with a pretty spectacular image. So I'm waiting for James Webb to do a real deep field image. Actually, I'm waiting for them to do any images at the moment, but they will do that within a month and a half or so. But I really want to see them do a deep field image. Now, remember, when you look at an image like this, the image is flat, but every telescope is a time machine. You're looking back in time. So you're going from the galaxies of today and looking back towards, in this pink region, this is, pre-CMB, and then you get the CMB and the first galaxies and stars forming, and then galaxies begin to grow bigger and come this way. So with that in mind, what you see, remember, here's a detail in the Hubble Deep Field. We saw this image before, the Hubble Deep Field North. These obvious spiral galaxies here and here, or the elliptical galaxy here, they're far away, but they're relatively foreground objects. They're not really high redshift objects. They're close enough that Hubble can get good morphology on them, but they're not really high redshift objects. But if you look around, there's a little blue dot there, and there's a barely visible dot there, tiny red dot there. These are really high redshift, very far away galaxies. You're looking back in time. One of the goals of the James Webb Space Telescope is to look at how galaxies evolve, how they change with time from high redshift to low redshift. But Hubble has already beaten them to part of that show. Here's some more detailed images of the deep field, where you can see really impressive spiral galaxies and little smudges, edge-on galaxies, irregular galaxies. There are tadpole galaxies, just about every kind of galaxy you can think of. But this is the real point. This is from the original ultra deep field. Here is that same yellow spiral galaxy you've seen before, relatively nearby. And these images are stepping back in time to higher and higher redshift, where these little red dot at the end is basically a redshift 10 galaxy, about as far back as you can look in the ultra deep field. And this is probably a redshift 1 galaxy or something like that. It's relatively nearby, close enough for you to get good morphology, tell that it's a spiral galaxy. As you go back in time, they look a little bit more mottled. This galaxy here does not have nice, clean spiral arms. It looks kind of like a spiral galaxy, but it's kind of messed up. This one looks like a spiral, but it has it's smaller. This is just irregular. It's hard to tell if you're even looking at one galaxy. Maybe you're looking at two interacting. And likewise, this is either an irregular galaxy or maybe two galaxies interacting, and this is just too far away, too small to see anything. Well, the theory is that galaxies form very tiny, And big galaxies like the Milky Way form because lots and lots of tiny galaxies come together. And my finger landed on the arrow and changed my slide. So there you are. We'll do it again. Here is from the legacy deep field, the big field. And again, you're looking back in time. And now this time they're giving you a distance. This is a light travel time distance. So 0.55 billion and 2.7 billion light years away. And even back as far as maybe 6 billion light years, you're getting a pretty good image of the galaxy. You can see what you're looking at. You can see that at 4.2 billion light years, it's still a spiral galaxy. You can see you're looking at an edge-on galaxy probably at 5.3 billion. By the time you get to 6, you can see the shape, but you can tell that it's irregular. And as you march farther and farther back in time, light travel time distance, and I put the redshift under some of these so you can get an idea what the correspondence is between redshift and distance. When I started my career in 1981, a redshift of 1 was a really high redshift. Now we're getting redshift 10, 11 galaxies all over the place. But you can see the same thing. The galaxies are all small and they're all irregular at high redshifts. And there's a lot of galaxies that are big at low redshift. And the idea is that big galaxies form by combinations of these littler galaxies. James Webb Space Telescope is supposed to flesh out this view of galaxy formation, but Hubble is already looking back 13 billion years into a universe that's 13.8 billion years old. So James Webb's main goal is to check out that last 0.8 billion years that you can't see easily with the Hubble Space Telescope and figure out what's going on. How did the very first little galaxies form, and how do they begin to form bigger galaxies? And of course, the Hubble Space Telescope has a 2.5 meter aperture, and James Webb has a 6 meter aperture. So James Webb should be able to have higher angular resolution, should be able to give you a better look at what these, even the same galaxies look like. If you stare at the same field, get even better structure. This is an image that I use in my How Big is the Universe talk. You're looking at the Hubble Ultra Deep Field. Remember, I said the galaxies that cosmologists look at are smudges, and those little things up at the top in the grayscale panels, those are smudges, and those smudges correspond to the little boxes in the main field. So here is an 8.6 redshift galaxy, the first one in the line. And if we look down in the image, way down here in the corner, where you see virtually nothing in this little purple box, that's where that smudge is. And so when you see an image like this, we're all impressed by how great the galaxies look, but the cosmologists are throwing all that stuff away and looking for the little smudges in order to see how far back they can go. And I won't spend a lot of time on it, but I talk about this. And when I talk about cosmological distances, the distances that everybody gives you, which are the top column here, the top row, 13 billion to 13.28 billion light years. That's a light travel time distance. You know what the speed of light is, you know how long a year is, you can turn that into a number of miles and get a distance, and you can treat the light year as a unit of distance in that way, and we commonly do, speak of it as a unit of distance, but it's not. It really is not. It is a unit of time. It's the amount of time it took the light to get to you. But if you want to know how far away something would be if you could stop the expansion of the universe right this instant, and walk there with a yardstick and pace off the distance, that would be the second group of distances. The actual distance, the way you think of distances, how many rulers do you lay out to get there, is this 30 to 32 billion light years worth of miles in distance. So this really is a unit of time up here, and this is the real unit of distance. And these other distances are associated with other ways of thinking of a distance. If you know the angular diameter of something, you can get a distance. If you know how light decays with inverse square relationship, so that if you double the distance, you cut down the brightness by a factor of 4. And if you 4 times the distance, you cut down the brightness by a factor of 16, and so on. So if you know the true brightness and the apparent brightness, you can get a distance. That's what the bottom group of distances is, 290 billion light years to 400 billion light years. It's called the luminosity distance. And when the gravitational wave people at LIGO give you a distance to their sources, they're always giving you luminosity distances, which will be slightly different than the light travel time distances. For just a few billion years, it's not going to make much difference. But if you're talking about nearly 13 billion light years, it makes a huge difference. But we don't see this kind of thing in anything but these ultra high exposed deep field images. Pretty much the only places that you can see high redshift galaxies like this. Otherwise, people find them gravitationally lensed. The Hubble Space Telescope will look at a galaxy cluster and find a lensed galaxy, but it's all distorted and screwed up by the gravitational lensing, and it's hard to figure out what it really is. Here, you can just see it directly, and it's not gravitationally lensed. And that's the talk that I put together this afternoon, and hopefully it's good enough to satisfy everybody.
Wonderful, absolutely great.
In the universe. I'm done. Thank you.
As usual, just amazing.
Well,
Thank
I'm
you,
glad to hear that.
Are you fielding questions?
Sure. Questions.
Look in the chat, see if there's any there.
I had that one question. It's kind of weird because David answered. Hubble can't make up for certain wavelengths that it's just not designed to do, right?
Right. Yeah.
No matter what instrument is installed.
That's right. So Hubble works primarily in the near infrared and near ultraviolet. So the longest. Yeah.
That's why we had to do the beryllium thing, right?
Yeah. The longest wavelength Hubble can look at was around 2 microns at one point with NICMOS, I believe. The James Webb Space Telescope goes out to 28 microns. Like Spitzer, its primary mirror is made of gold-coated beryllium. Gold reflects infrared much better than silver. The Hubble mirror is a super low expansion glass, silver coated. So it's not optimized for infrared observing. To look at super high redshift galaxies, you probably cannot see them with Hubble because the redshift pushes the wavelength out so far that there's no instrument sensitive to it. And even if you had an instrument sensitive to it, you'd really rather have a gold coating than a silver coating.
Thank you. Do you think there'll be a lot of, I don't know how to put this, NASA false color images, or is JWST really not capable of that kind of thing?
James Webb is essentially incapable of visible light images. The shortest wavelength that James Webb can look at is just a little bit blue of the hydrogen alpha wavelength. I think hydrogen alpha is around 6.6 or 6.8 microns. I can't remember. Somebody out there maybe have it in their brain. but it's close to 7 microns. It's in the high 6 microns. And the shortest wavelength James Webb can see at all is just a little bit blue from hydrogen alpha, because it's a useful wavelength to have. So you want to be able to see hydrogen alpha.
Thank you.
Yeah, none of the
Wonderful
normal
presentation. Thank you again.
Thank you. None of the normal visible light will be seen in James Webb images, and it goes out to 28 microns. And so all that's going to be false color, and the color will be tuned maybe to the channel the instrument's observing with, or what molecules they're looking at, something like that.
Now, Tim, on the Hubble Deep Fields, I can't remember, but those are also false color too, right? They're not. They didn't try and deliberately balance them. So this would be an eye view of these galaxies and their colors.
Well, both the deep fields were mostly visible light, so I think those are realistic colors. I'll just make you dizzy. Are you dizzy yet? Okay, there. So human vision extends from roughly, say, 350 nanometers to about 700 nanometers. So the blue channel and the red channel are beyond visible, but the 450 and 606 channels are visible. And they probably made these images with the colors representing the channel. And so it's not going to be really true eyeball color, because 2 of these channels are eyeball invisible, but they're pretty close. James Webb, they just have to make stuff up. Michael Hayford, you got your hand up. So go for it.
Thanks, Tim. So did they identify blobs that they were interested in and then do spectroscopy on those to get the distances, or what did they do?
I think the distances are mostly photometric redshifts. And so some of them, yes, they did identify them in the Hubble ultra deep fields and then observe them from the ground where they could. But you can't do really long wavelength infrared from the ground. The atmosphere is opaque, even from places like Mauna Kea. You really need to be on Sophia flying at 40,000 feet or something in order to see really long infrared wavelengths. So there will be a lot of new stuff coming out of JWST where they can and will do spectroscopy all the way out to 28 microns. So a lot of the distances that come out of Hubble, which are photometric redshifts and therefore lacking in precision, will be spectroscopic redshifts coming out of JWST. And
I know
if there's
the Atacama Desert is not as high as Sophia, but is that also an infrared area?
no, it's too low.
Completely the opposite, right?
Yeah. Atacama is around 16,000 feet. That's still too deep into the atmosphere to see infrared. The millimeter waves get through, and the submillimeter waves, like 800 microns or something that the Herschel Space Observatory did. But infrared, like we're talking about, will not penetrate to that depth.
Thank you.
Have to
Got
be
it.
Yeah.
I was not sure. Some of these wavelengths all get mixed up in my head.
All you need to do is become a professional astronomer. You see, now, when I worked in radio astronomy, we always talked about frequencies, gigahertz and megahertz. The optical astronomers always talk angstrom units. The infrared astronomers talked wave numbers, which is the inverse of the wavelength. And you're jumbling so many units around in your head, you just can't figure out what the other guy's talking about. You have to wait a minute while I get out my paper. That's I see what that is. That's so many centimeters. it drove me nuts. It just constantly shifting units
Not
around.
sure at 63 times around the solar system or the sun, I'm ready to do that. Become a professional.
Yeah, why not? Everybody needs a new career. Go for it.
Is there any possibility that SpaceX may, or somebody else may someday do a maintenance trip out to Hubble?
Elon Musk has already said that he intends to do that. The Crew Dragon that flies to the ISS as it stands is not capable of doing that. It can't support EVAs, as far as I know. It just flies up and flies back. We don't have anything that can support an EVA. So he's going to have to build another capsule. He says he's going to do it. But Elon Musk says a lot of things. He said he was going to buy Twitter and he did it. So I don't know.
Yeah, exactly. It'll be the Twitter Space Telescope.
Could be.
Tim, looks like Don De Grigori had his hand up.
Yeah.
Oh, I
good
can't
evening,
see.
Tim and everybody.
Don.
I've been around for a long time.
Yeah.
Can you hear me okay?
Yeah, I can hear
Yes.
you.
Okay.
Yeah.
Tim, I wonder, James Webb actually wants to find that 0.8 billion mile gap at the end. In other words, Hubble can go out to 13, but not 13.8.
Yeah.
Now at 13.8, as James Webb looks further past 13, what will it see at Big Bang point?
Well, it's a good question. JWST can see out to 28 microns. The galaxies we're seeing from Hubble now that are about redshift 10, redshift 11, look at the universe around 300 million years, that's millions with an M, after the Big Bang. But all the interesting stuff goes on before that. James Webb should be able to look out to redshift 20, which will get us to 200 million years after the Big Bang. The project scientist, John Mather, says they should be able to see out to redshift 30, which would be really impressive, which would take us to 100 million years after the Big Bang. But that 100 million years gap covers a redshift range from 30 to about 1100, which is the redshift of the cosmic microwave background. So digging into that last 100 million years is going to be really hard. But at redshift 30, we really should be able to see the first stars and the first galaxies forming. Of course, I've heard that before with the Hubble Space Telescope and other things. We should be able to see that. If we do, everybody will be happy because it will at least give us an opportunity to see how the first stars and galaxies form, and will tell us that we've got the story about right. That's, that our current cosmological models are not completely insane, that they kind of work. If in fact we look that far back and still can't see the first stars and galaxies forming, then we are in trouble. Then our cosmological models are insane at some point, and we have to do some serious work to figure things out, because 100 million years after the bang is not much time to start forming stars and galaxies. There you are. Yeah. Yeah, I can't see everybody who's got their hand up. I can only see like 5 or 6 panels here. So if somebody else sees somebody, or just speak up, ask away.
I think we've exhausted questions. Tim, thank you. That was awesome.
Oh, okay. Thank you.
Everyone can unmute if they want to say hello again.
Hello, Tim. Thank you so much.
Yep.
Thank you.
Yay.
Apropos, nothing.
Thanks, Tim. Thanks, Tim. That was great.
Yeah, thanks.
Thank you.
When I was in Silicon Valley, my secretary's husband was an astronaut, and he launched the Hubble from the space station.
Ah,
His first mission. He made 3 missions to the space station.
yeah, Hubble was Hubble Space Telescope was launched from the Space Shuttle.
Oh, I'm sorry. Yeah,
Yeah.
yeah. He made three shuttle flights.
Cool.
He now teaches astrophysics at Kansas, I think.
You see that all worked out great because you don't want to go down in history as being on the space shuttle crew when they got the Hubble Space Telescope out on the arm, and then somebody just kind of dropped it, thump, and then you don't want to go down in fame as the guy who dropped them. They just leave you out there and come back without you.
Okay, has everyone signed up for the drawing? And Spencer, I didn't see Alicia here.
No, she said she was ill and she couldn't make it, and could somebody take over?
Okay.
Yeah,
So,
she emailed a list of the prizes.
Oh, she did. I didn't see that.
Yeah, I've got it written down. If
Do you want to take care of that, Tim? I didn't see it, so.
I guess I can do that if, but of
You have a
course,
list?
yeah, Spencer's got to.
hang on. Let me. So everybody's seen the. Everybody signed up. I'm going to close it out. There are 29 people on the session, and 26 have signed up for the drawing.
I just signed on a couple of minutes ago. I don't know if it's instantaneous for you or
Yeah,
not.
it probably is. So let me just. Okay, well, we'll give it about 30 more seconds, and I'll close it out.
How do I sign up?
There's a link that I posted in the chat. Let me repost it in the chat.
Yeah.
Hang on, let's see. Okay, it's in the chat.
Could you add me, please, or should I?
Well, it's probably better if you click on the
Hey,
link. 'Cause
John?
if I add you, then I have to go through a lot of.
Don, go to the chat window on the screen, on the side of your Zoom window,
Well, I see.
and you'll see a
something-
drawing link. Right.
Oh,
It says chat, click on chat.
okay, here I go.
When you click on chat, you should see the last entry. It says drawing link, and there's a link. Click on that link. It'll take you to a website and allow you to sign in with your name and email address.
Oh, there you go. Okay, I see it. Thank you.
Cool.
So I tell you, Zoom can do lots of strange things, as everyone knows, and I always think I'm going to lose everything.
Yeah.
At least it works the same time every time. I'm giving 2 talks in the near future using WebEx, which I've used once before. And WebEx has never behaved twice in a row the same way. Literally, I have to reinstall the software every single time. It behaves different. It's crazy.
But Tim, didn't we say that about Zoom for the first 6 months as well?
Yeah, maybe,
don't
but
think so.
Zoom at least is stable. It behaves the same way. You don't know how it behaves, but it behaves the same way every time.
Every single time.
Okay, I've closed out the drawing, so I'm just pulling the list now.
Okay. Did you get a chance to do your thing, Don?
I just did it when he said we're closed out. Whatever.
You
Yeah,
watch,
look and
Don.
see-
You're going to be the first winner.
Yeah, look and see if Don's name is there.
Okay, hang on just a second. Let me. Let's see, where's.
Hey, Liz, nice to see you here.
Hey, Daryl, nice to see you.
Uh-oh. Now I lost everything. Oh, gee.
Nice to be seen.
Oh,
You
Hey,
busy
Daryl?
girl.
Daryl,
Yes.
Steve. while they're doing this, you might want to fill people in any word from Griffith or from Mount Wilson about any upcoming possibilities for star parties, or have you heard anything at all?
Well, I think. Well, I got an email from Maggie. It was kind of last minute though, asking me if anyone wanted to come up and set up telescopes for the lecture. I think only one person showed up, but probably because short notice. So I'm assuming that if they want to do that at any of the lecture events, they're going to want some volunteers to come up and set up scopes at the 60 and the 100 both. So we can pretty much count on that. I think it was just a late call on that one, so we didn't get much of a response.
Hey, quick question, if we have 1 second. I'm sorry I missed the beginning of the meeting. Do we know the date for next month's star party? I'd really like to schedule around it for once instead of suddenly realizing I couldn't go.
You mean the dark sky night?
Yeah, Tim, sorry, yeah.
Yeah.
It's
I
always.
guess I don't.
Because I think it's Memorial Day weekend, and that's why I'm asking.
Aren't those on the calendar from the webpage?
Oh, are they in advance?
Yes. Yes. They should be.
Yep.
Okay, sorry guys, I didn't realize that. I'll go find the calendar.
Okay, I'm ready to withdrawing. Let me just share my screen then.
Tim, you ready on the other end there? Okay.
I'm ready. Just give me enough time to scribble down the names of the winners, before you erase them.
Okay. All right. Okay. Oops, sorry, wrong thing.
Not that screen.
Wrong screen.
You're sharing your Facebook screen.
No, that's
Oh, nice pictures.
It's an infinite regression of Facebook sharing.
Really? That wasn't me. I wasn't sharing that.
We're just picking on you.
Okay. All right. Here we go.
It's empty. There it is.
All right. So Jameer is the first one.
First winner.
Okay, and what's Jameer's last name?
Let's see. He didn't put a last name.
Oh, okay.
We're gonna
Good.
need that.
Okay.
Is he still? Yeah, he's here. But let me see. I think I have his email address. Let's
But
see.
yeah, as long as we have an email address, then.
Yeah, I have the email address. Okay. All right.
Okay.
Oh, hey, thanks.
Okay. So what did he win?
What did he win?
He won a $25 Amazon gift card.
Yay.
Okay.
And the next thing we're going to draw for is an LAAS hat.
All right.
Thanks, guys.
Okay. Claude.
Claude Plymate. Claude, you get a hat.
All right, Claude.
All right. Next is
Next thing we're going to draw for is a laser.
Oh, I've been waiting for a year. Come on, come on.
Phil Taylor.
Nope.
Phil Taylor. Wow. Phil gets a laser.
Okay.
All right, Phil.
The next thing we're going to draw for is a Celestron observer's map of the moon.
Okay, this is Justin Hawkins.
Justin Hawkins. Okay. Isn't that one of
Yeah,
our
all
new
right.
members? Cool.
Thank you.
Now you can
All right.
observe the moon. The next thing we're going to draw for is a red flashlight.
Tom Hendricks.
Okay.
Wow,
We only
thank
have
you, everybody.
1 minute.
All right. How many more do we have?
Hendricks, RICKS. We have one more, and that it will be an item from the LAAS store.
Okay. Elizabeth Wong.
Yay.
Yay.
Elizabeth Wong. Okay.
So you go to the website in the web store.
Oh, great. Thank you so much.
Cool.
I love it.
Lots of cool things there.
Okay. I've got the names.
Okay.
And
We're out of prizes.
I'll I'll send, if you don't already have the email addresses, you can send me. If you didn't save the names, I'll send them to you and you can send me the email addresses. Or
All
just
right.
send the whole thing on to
I'll
Alicia.
yeah, we'll send, why don't you send me the names and I'll send the names and email addresses to Alicia.
Okay. Got
Very
it.
good. Okay.
And so the project scientists for the GMT, who are Giant Magellan Telescope, I was trying to get to speak, finally answered me about an hour before the meeting. She was off traveling somewhere and catching up on her email, and of course couldn't do tonight, but said she would send me names of people who could. So I'm going to try, we'll see if it works, to get somebody to talk about the Giant Magellan Telescope for the next meeting. And we've had talks about the 30-meter telescope, but they're still frozen on Hawaii. And I'm beginning to think they're going to have to just move to the Canary Islands. I don't think they will be able to build on Hawaii at all. So but the GMT, they've made all the mirrors and they're digging dirt and they're building the building and they're actually going to be working by 2025 or 26. So they're the ones that will actually be doing something. So I'm nice to have a talk from them.
Great. All right.
Excellent.
Okay. Well, if there's no other
And
questions
our
for
members-
Tim, we can just chat, but we should probably, if we're done with everything, we can end the meeting officially.
Yeah.
Everyone's welcome to stay and chat.
Okay, so I'm going to